Every server, every massive database, and every cloud application eventually relies on physical spinning disks or flash memory. But a single hard drive has a hard physical limit. It can only read and write data so fast, and eventually its mechanical parts or memory cells will fail. To get around those individual limitations, we use RAID, a redundant array of independent disks. It takes multiple physical hard drives and links them together, so your computer treats them as one single, highly capable logical unit. But linking drives together forces a critical decision. Set up your array incorrectly, and you might throw away half your hardware budget on protection you don't actually need. Set it up a different way, and a single hardware hiccup could permanently wipe out your entire system. This chart shows 3 pillars: performance, distributing commands to increase speed; redundancy, surviving drive failures through backup math; and capacity, maximizing usable storage space. You cannot maximize all 3 simultaneously. Pushing for speed and space sacrifices safety. Demanding total safety surrenders capacity. To navigate this, RAID manipulates your data using 3 core techniques: striping, chopping data into distributed blocks; mirroring, cloning identical backup copies; and parity, calculating protective recovery math. You aren't looking for the best RAID technology. You are negotiating a strict operational compromise based exactly on what your data is worth. We'll start with the extremes. This animation shows RAID 0, or striping. When you save a file, the system breaks the data into chunks and writes them across 2 disks, alternating back and forth in parallel. Because you have 2 or more disks working at once, read and write speeds skyrocket. Plus, you get to use 100% of your physical storage capacity. The trade-off is absolute zero fault tolerance. If just one drive fails, the chunks on the surviving drives become unreadable fragments. You lose all your data. The exact opposite approach is RAID 1, known as mirroring. Here, the system writes identical, full copies of your data to both drives at the exact same time. This provides total redundancy. If a drive dies, the other one doesn't skip a beat. Your system stays online with 0 data loss and instant recovery. The cost here is a strict 50% capacity tax. If you buy 2 4-terabyte drives, you only get 4 terabytes of usable space. You are paying double for your storage. RAID 0 and RAID 1 represent the strict boundaries of storage architecture. You either completely sacrifice safety to maximize speed and capacity, or you sacrifice half your hardware budget to guarantee total protection. This animation illustrates RAID 5, designed to bypass that massive 50% capacity tax. This setup requires at least 3 disks. As it distributes your data, it writes a calculated value, called parity, alongside your files. Notice how the parity block shifts to a different drive for every row. That parity math is your safety net. If a drive dies, the system uses the surviving data and parity blocks to reverse engineer the missing information. You achieve your redundancy, but you only lose 1 drive's worth of total capacity across the entire array. The catch is performance. Calculating that parity math on the fly requires continuous processing power, which visibly penalizes your write speeds. The critical risk, however, occurs after a failure. Rebuilding that missing data from parity takes a massive amount of time, often days for large arrays. This process stresses the remaining hardware to its absolute physical limits. Very often, that heat and sustained mechanical stress cause a second, older drive to fail right in the middle of the rebuild window, wiping the entire array. To prevent that scenario, engineers use RAID 6. It functions just like RAID 5, but as you see here, it calculates 2 independent blocks of parity for every single row of data across a minimum of 4 disks. Now, your array can survive 2 simultaneous drive failures without losing a file. The trade-off is steeper. You permanently lose 2 full drives of capacity, and the extra math slows your write speeds down even further. Parity offers a highly efficient middle ground between capacity and protection, but you must accept the complex math bottlenecks and the dangerous rebuild windows that come with it. If your operation cannot tolerate slow math or risky rebuilds, you use RAID 10. This requires a minimum of 4 disks. The array first groups them into mirrored pairs. Then it stripes your data across those pairs. You get the extreme read and write speeds of striping, combined with the high redundancy of mirroring. And if a drive fails, the rebuild is fast and low stress, because it just copies the data directly from its surviving twin. The penalty is maximum hardware cost. You are permanently losing 50% of your total raw capacity, demanding a high budget for large datasets. This visual shows what happens at the enterprise scale. Nested parity levels, like RAID 50 or 60. Here we have two separate RAID 5 clusters, with an overarching controller striping data across both of them. This lets corporations scale up to enormous storage capacities, while keeping read speeds high. Crucially, it isolates drive failures. A single broken drive only forces a rebuild within its specific smaller cluster, rather than stressing a giant multi-terabyte array. But these nested setups feature extreme complexity. They require absolute minimums of 6 to 8 disks, making them strictly suited for high-budget corporate storage. At this level, enterprise environments aren't looking for clever compromises. They are throwing raw hardware and money at the problem to buy their way past traditional bottlenecks. Knowing how the data blocks drop is useless unless you map the technology to your specific scenario. This flowchart starts with the determining question: what is your primary priority? If you are running a video editing scratch disk where raw speed is the absolute priority, redundancy doesn't matter and your files are backed up elsewhere, you use RAID 0. If you are building a home media server or a general file archive, and your goal is massive storage capacity on a budget with basic single drive protection, you go with RAID 5. If you manage a mission-critical database that requires highly transactional speed and zero rebuild downtime, you pay the hardware tax and deploy RAID 10. And if you are architecting massive enterprise arrays, where rebuilds take days and double drive failures are a probable risk, you choose RAID 6 or 60. But no matter which path you select, you must recognize one overriding rule. RAID is engineered for hardware uptime and system availability. It is not an archive. If a power surge hits, or ransomware locks your files, or someone accidentally deletes a folder, RAID will instantly and perfectly replicate that destruction across every disk in your array. Regardless of your hardware budget, a separate offline backup is the only true way to protect your critical data.